Here we want to find the electric field acting at a particular point in space due to two charges that are around it. One thing about electrical field that you need to know is that we assume that the point in space is like having a test charge of a positive charge value. So whenever there's a positive charge around it affecting it, we assume that the electric field points away from that positive charge because the test charge is also positive, and so there's a repulsion. If there's a negative charge, then we assume that the electric field points towards the negative charge as if the test charge is positive, being attracted to the negative charge. So similar to the force equation, we're going to write out the electric field equation, which ends up just being KQ over R squared. All right, and so to write out the electric field at point A as a vector. That's going to equal to the electric field at A due to 1 as a vector, plus the electric field at A due to charge 2 as a vector. Again, because this is a two-dimensional problem, let's break it up into X and Y components. So we're going to go ahead and say the electric field at point A in the X direction is equal to the electric field at A due to 1 in the X direction, plus the electric field at A due to 2 in the X direction. And again, we use the absolute value signs because we want to have complete control over the sign in which the electric field at point A is dealing with. So at point A, charge 2 is going to have absolutely no effect because it's right underneath point A. So there's no X direction in which charge 2 is affecting the space at point A with its field. So we say that the electric field due to charge 2 at point A is 0. Now, due to charge 1, as we can see, it's a negative. So that's an attractive force. So therefore, the field goes to the right. And based per our convention here, we say to the right and up is positive. So this has to be positive since the field is going to go to the right towards Q1. Due to, again, alternate interior angles, we're going to see that the angle that Q1 is below below point A is just 30 degrees. So to get the X component of Q1 at point A, you got to take SOHCAHTOA, and cosine works for adjacent legs to the angle of 30 degrees. That happens to be, in this case, the X component, and so the X component is going to be a cosine. This then equals to cosine, so it's positive, cosine 30 times K, Q of 1, divided by the distance between point A and charge 1 squared. In the calculator, this ends up being positive 1081328.942, so very long number. We're going to go ahead and reduce it down to the appropriate number of significant figures. That's going to be 1.1 times 10 to the 6th power newtons. In the y direction, we're going to do the same thing. The electric field at A in the y direction net is equal to the electric field at A due to charge 1 in the y direction, plus the electric field at A due to charge 2 in the y direction. Now, let's go and analyze what's going on. Charge 2, the y component is, there's the y component from both charge 1 and charge 2. Charge 1 is going to try to pull it down, and charge 2 is going to try to pull it or push it up. So it looks like this term is going to be a negative and this term is going to be positive. Let's go ahead and write out the more robust terms. That's going to be negative in this case. And we're going to use sine because we're doing a y component. So the leg of the y component of the electric field acting on A due to charge 1 is opposite of the 30 degrees in that force triangle. So it's going to be K Q1 over RA due to 1 squared, plus there is absolutely no trigonometric function here because Q2 is right underneath point A. So it is going to be K Q2 divided by RA2 squared. The terms ends up being negative 624,305.5556 plus 4994444.444. Okay, so this is just the root calculation here. To add them up, it ends up becoming 4370138.888 newtons. If you were to simplify it into the appropriate number of significant figures, which is 2, it ends up being 4 point, we round up, 4 e to the power of 6 newtons. That's going to be the electric field at point A in the y direction. And this is going to be electric field at point A in the x direction. Now for simplicity, I'm going to skip part B because it's actually almost the same in terms of the procedure.